Yeah, so we have just seen that the gap opening is due to this possibility to use a combination of plane waves to describe the actual wave function of the electron. And just to see another meaning related to the position where we observe the degeneracy removal, in general, the removal is observed when we have that different branches um, has the same energy value. So if we take, for instance, the let's say the first branch is described by the parabola of Sommerfeld, let's say. So in the first branch, we have an energy dependence that is described in this way, and that comes from the parabola that is centered in the first Brillouin zone. Then we also have the we may consider, for instance, the intersection between the parabola in the first zone and the parabola that comes from the second zone. So in this case, this is equal I call that G. G is a vector of the reciprocal lattice. So in this case, G is the, let's say, center of the second zone, and K is the variable. So in this picture, we have that these two values are equal when we have the degeneracy. So at this point, what is the effect of that? If we, let's say, simplify the Planck constant, the reduced Planck constant, and the electron mass, we have that k squared is equal to g minus k squared. So we have k squared is equal to g squared plus k squared minus twice the scalar product of k and g. So if we remove k squared, we have that g squared is equal to twice k scalar product g. If we replace g by a versor of g times the modulus of g, we have that on the left side, we have the square modulus of g. So we may simplify one modulus, and we have that g modulus is equal to twice k scalar product g versor, or k scalar product g versor is equal to g modulus divided by 2. And this is the equivalent of the Bragg condition to observe, let's say, if you, now we are considering that G is a vector of the reciprocal lattice and K is a wave vector of the electron. But if just for a while we switch to another picture, that is the picture where the Bragg description or the von Laue description try to understand why we have scattering of plane waves, of electromagnetic waves by the lattice. In that picture, K was the wave vector of the electromagnetic wave, and G was the vector belonging to the reciprocal lattice. So this is the same equation that was obtained when describing the scattering of an electromagnetic wave having a wave vector equal to k by a lattice described by a reciprocal vector equal to g. So we have exactly the same condition, apart from substituting the wave vector of the plane wave by the wave vector of the electron. So in this picture, you may see that, let's say, what is observed is that you have degeneracy and also gap opening when the wave vector of the electron satisfies the condition to so that a plane wave with that wave vector is able to let's say satisfy the Bragg condition for that specific lattice. So in this picture, if we let's say we use the free electron energies, so in this picture the electron is a plane wave, and in this picture again the electronic wave undergoes a sort of Bragg diffraction by the lattice where the electron is moving. So this is another way to let's say another comment concerning what happens when we have the degeneracy. What are the conditions that are met? And in the first case, we observed what is the effect on the energy. In this case, we observe the effect concerning the electron considered as a wave, as an electromagnetic wave going through the crystal. And if you notice, once you have the opening of the gap, always in this one-dimensional picture, we have this modification. So in the initial branch, the derivative depending on the derivative of the parabola. In this condition, the derivative is zero, close to the border of the zone. Oh, sorry, close to the border of the first Brillouin zone. In this one-dimensional picture, what does derivative equal to zero means? That means that if we consider the velocity of the electron as the velocity is the derivative of the energy with respect to k, in this picture here, the velocity of the electron along the horizontal direction is equal to zero. So what we have is that in the one-dimensional picture, the velocity of the electron in the direction of the border of the zone, that is the direction described by the vertical line, is equal to zero. If we now want to extend the same information to the three-dimensional case, what we have is that the velocity of the electron in general in 3D in the direction of the border of the zone, and in this case the border of the zone is not a line but is a surface, that velocity has to be equal to zero. So if we go in 3D, the velocity of the electron so the again, the component of the velocity in the direction that is perpendicular to the surface, to the border of the zone, has to be zero, due to the fact that the velocity is the gradient of the energy. If the velocity has no component orthogonal to the border of the zone, this means that the velocity is parallel to the border of the zone. So due to the fact that the velocity is the gradient of the energy, this means that the gradient of the energy has to be parallel to the border of the zone. Is that fine? Okay, so the gradient of E has to be parallel I just wrote parallel to the surface of the first zone because then for periodicity, any zone is equivalent to any other zone of the lattice. So I just pick up the first zone as a reference. And just to use the names that are used also in the textbook, as we saw, thanks to this equation, the when we observe the degeneracy, and in this case, the degeneracy is observed exactly at the border of the zone, the Bragg condition is met, then this line here, or in 3D, the surface that is the border of the zone is called, that surface is a plane, and that plane is called the Bragg plane, because the Bragg condition is met over that plane. So in 3D, so the surface of the first Brillouin zone in 3D is not a continuous surface. In a while, I'll make a picture of that. Is a combination of different planes. In the case you have a cubical lattice, you have 6 planes, front, rear, left and right, up and down. So these 6 planes that are the surfaces that represent the surface of the first Brillouin zone are 6 Bragg planes. So this is important as the, let's say, in general, if we have only free electrons, the gradient of the energy has just spherical symmetry, the k-square dependence. So in that case, the gradient of the energy is independent of anything else, but depends just on the energy function. When we switch to the block picture, the gradient of the energy depends both on the value of the wave vector and on the presence of the Bragg planes. When the energy surface is close to a Bragg plane, then we have a distortion. In 1D, the distortion is the one represented here. So this modification of the derivative close to the border of the zone. When we are in 3D, the deformation may depend exactly on the direction of the plane and on the orientation of the energy surface. So in general, the situation is slightly more complex with respect to the one-dimensional case, and the complexity depends on the fact that we have to consider, when designing those surfaces, we have to consider the orientation of the planes, and we have to take into account the interaction between the energy surface and the Bragg plane. I would just like to make an example of that, just to fix everything. And since it would be best for me not to make plots in 3D, I just make the 2-dimensional situation. And now, let's say, I'll try to do my best to make the picture as clear as possible, but please use your imagination. Let's say, combine my picture with your imagination so to have a clear picture of what is happening. And as usual, I will refer to the cubic lattice, because in the cubic case, the first Brillouin zone is just a cube, so it's easier to make the picture. As soon as we conclude the discussion of the 4 points that I presented to you before, I will show you the actual results of the calculations. So we will see the effect of this distortion also in case we consider BCC and FCC lattices. But that is quite complicated to draw here. So here, for the moment, just cubic lattice. Okay, so let's try to imagine what may happen to the different energy surfaces when we consider the interaction of those surfaces with the Bragg planes. So first step, let's suppose to work in the reciprocal space. So we have the origin, and let's suppose we start from the free electron picture. So first step is just free electrons. At this point, if we have free electrons, we know from the Bohr-von-Kammer boundary conditions what are the levels that the electrons may occupy. The energy is spherical, as spherical symmetry. So at this point, when we include the electrons in this system, in this picture, what we have is a sphere. So we end up with an occupation that has a spherical symmetry, and so we have the we have more or less a sphere. Yeah. So this is the first step. Let's suppose to have 3 electrons. At this point, we have to consider that if we switch on the potential, then we may have a deformation of this surface. In particular, the interest is always concentrated on the Fermi surface. So this sphere represents the Fermi surface. Now we need to consider the interaction of that surface with the Bragg planes. So we need to consider the fact that here in the reciprocal space, we have the reciprocal lattice, and the reciprocal lattice, in the case we have a cubic lattice, can be represented in this way. So we have a square lattice here. How may we build up the Bragg planes? In the calculation that was presented before, the Bragg plane corresponds to is a plane that is perpendicular to a vector belonging to the reciprocal lattice and cuts that vector into 2 parts. So I use that method to construct the Bragg planes, and so to single out the first Brillouin zone. So if I consider this vector, this is one of the vectors. No, one step back. This is not an arbitrary vector. This is, if you consider the origin, this is one of the next neighbors. So if you suppose to stay at the origin in this lattice, in this square lattice, you have 4 next neighbors. And the 4 next neighbors are 1, 2, 3, and 4. So now I use the method observed before to build up the 4 corresponding Bragg planes. So I divide this vector into 2, and I plot here the line corresponding to the half of that vector. I do the same construction with 2. So half of that with 3, half of that, and with 4. So in this way, what I have found is a square, and this square is the first Brillouin zone. Then what I may do is to consider the second neighbors to find the second zone. And the second neighbors, so 1, 2, 3, 4, are the first. And then five, six, seven, eight are the second neighbors. In this case, I use exactly the same method, that is the following. So I connect, for instance, with 5, divide into 2 parts this vector, and then I draw. Okay, and what happens now? The first zone in this diagram was a square. How do I find the second zone? The second zone is represented by the regions of this space that I may reach when crossing just one plane. So if I start from the origin and then I explore this space, the first zone is the zone where I stay without crossing any plane. The second zone is the zone where I stay after crossing just one plane, starting from the origin. So the only regions, the regions of space that I reach after crossing just one plane are this triangle, then this triangle, this triangle, and this triangle. So I have 4 triangles, and if you notice, those 4 triangles do not produce a square, let's say, are not actually a square. But if you translate back these 4 pieces using a vector belonging to the reciprocal lattice. So if you translate back those 4 triangles into the first zone, then you completely fill the first zone. So the idea is, in this case, the first zone is contiguous. So I single out the square, and that is the zone. Differently, for instance, in this case, the second zone is made of 4 pieces, but if you translate back those pieces into the first zone, then you again have an area that is exactly equal to the area of the first zone. And even worse is the situation of the third zone, fourth zone, and so on. So many pieces to consider, but if you translate all those pieces back into the first zone, then you completely fill the area of the square. At this point, we have, let's say, included the Fermi surface in between the first zone and the second zone. At this point, we have to consider the effect of the distortion. As we saw, the distortion is such that the gradient of the energy at the Bragg plane has to be parallel to the plane itself. So let's try to apply this, let's say, deformation to the spherical surface that I draw at the beginning, just supposing that the electrons are free. So in this case, here, where may I? Yeah. If you notice this point here, in this corner, I have that the Fermi surface is, let's say, approaching the border of the first zone, but the derivative of that, let's say, that surface is not orthogonal to the border of the first zone. So I have to deform that surface so to make that orthogonal. So I may do something like this. And the same happens to all the other zones. So here, okay. Mm, so this is the deformation of the outer part. As in some points, the sphere was also included in the first zone, then I have also a possible deformation So I have also a possible deformation of the small part of the sphere that was slightly included in the first zone. And in both conditions, I have that the profile of the Fermi surface is always orthogonal to the plane. You may ask me, why do you do that? So why do you expect that the surface should be orthogonal? Because in general, when you consider the free electron picture, as you move away from the center, the energy increases. So one generally expects that if you are at the Fermi surface, behind you, you have low energy levels. In front of you, you have high energy levels. So the gradient of the energy is orthogonal to the surface. Having this in mind, if the gradient of the energy is in general orthogonal to the surface, and I want that the gradient is parallel to the Bragg plane, I have to do a deformation such that the surface is orthogonal to the plane, so that the gradient to the surface evaluated close to the border of close to the plane is just parallel to that plane. So that's why I plotted um, the parts of the surface that are close to the plane as orthogonal to the Bragg plane. So at this point, what may I tell you about the actual shape of the Fermi surface? As we see here, the Fermi surface occupies two zones. One zone is the first zone, the other zone is the second zone. So at this point, to give you all the details concerning the shape of the surface, I have to give you two plots. One plot that corresponds to what happens in the first zone, the other plot that corresponds to what happens in the second zone. So let's start with the first zone. The first zone is a square. And in this square, the only portions that have a meaning for this plot are those portions very close to the corners. So in this case, we have that the diagram of the Fermi surface in the first zone is just a square, sorry, where let's say, the inner part of the square is made of occupied levels, or the levels are filled because they were within the sphere in the original plot. Close to the corners, we have empty levels. So those four regions close to the board, close to the corners of the square, are made of empty levels. Then what happens to the second zone? Also, the second zone is a square because all the zones have the same shape. But if you notice here, we have to obtain a square, we have to translate into the first Brillouin zone the four pieces of the second zone. So at this point, I have four triangles, one coming from the, let's say, one triangle comes from here, from the right, another triangle from the left, one up here, and the last one is below here. So if you take those triangles, you apply one translation to each triangle, and you bring the triangle back to the first zone, then you obtain a square. Now, what is the shape of the surface now after the translation? Let's take as a reference the triangle here that corresponds to 1. The triangle that corresponds to 1, when translated back to the first zone, appears here, because we have to translate by one side of the square, so one vector belonging to the reciprocal lattice. So the triangle corresponding to 1 is this triangle here. The levels, the occupied levels in the initial diagram are found in the left side of the triangle, so close to the base of the triangle. After the translation, the base is one of the four sides of the square, so we have that the levels are here. And applying the same method, we have those four regions. And where are the occupied levels? The occupied levels are within those four regions. So here we have so those four regions include the occupied levels, and the rest of the zone is includes just empty levels. So yeah. So to summarize, with respect to the initial spherical shape, or with respect to the initial circle, as we are in 2D now making these pictures, the actual shape of the Fermi surface is slightly more complicated. In this case, the Fermi surface occupies part of the first zone and part of the second zone. In the first zone, we have that all the levels are occupied apart four small regions that are close to the corner of the square. In the second zone, we have that the levels occupy those four areas. The occupied levels are in those four areas, and the rest of the zone is empty. Using the indexes that we observed before, this plot corresponds to n equal to 1, so first band. So all the levels in the first zone are the first band. This corresponds to n equal to 2. So all the levels in the second zone are band corresponding to n equal to 2. If we had levels in the third zone, then we need to use also n equal to 3. So in this case, we have that two bands are simultaneously occupied by electronic levels. And please note that in the one-dimensional picture, this was not possible. So in the one-dimensional picture, you have occupied or half-occupied bands. You have not the opportunity to have two half-occupied bands, as we have in this case. And please note another thing. In the first zone, if you start, let's say, if you are an electron that is in a field level, so if you are over an occupied level, and look at the surface that separates you from the empty levels, if you want to go in that surface, you have to move away from the origin, because if you are here, for instance, empty levels, and you want to move to the free levels, you have to move away from the origin. In the second zone, if you are in an occupied level and want to access the free levels, you have to go to the origin. So you have a different direction of motion of the electron. Now, you may ask me, why should I move if I'm an electron? And the answer is, at the moment, I'm not the element, say, I need something more to tell you why the electron should move. But in general, just consider that the orientation, if you want to access the free levels, then in this case, you have to go through the origin, not as in the first zone, away from the origin. And the last comment is, please note what is the direction of the gradient of the energy. The gradient is orthogonal to the surface. So in the first zone, the gradient point outwards, so out of the center of the first zone. In the second zone, for instance, here, or also here, the gradient does not point outward, but points inward. So depending on the band you consider, the direction of the gradient may change. And this means also that the velocity of the electron changes. So if the gradient changes direction, also the speed of the electron changes direction. So depending on the zone you consider, the direction of motion of the electrons is different, even corresponding to the same value of K. Yeah. Yeah, it's 11 o'clock. I think I will stop here, as Professor Moretti, I think, is coming. Yeah, I know that maybe this is not the best picture you may have in front of you, but I prefer to do that by hand, just to follow the same steps that you may do on your sheet of paper. So to do step by step the construction of this, the formation of the Fermi surface. And do you have questions or comments concerning this representation, or in general the today lesson? Thank you. Also here. Okay. Okay, so if you have not question or comments, then I stop here, and I will leave. No, I stop the connection now, and in a while, Professor Moretti will activate a new connection for his lesson. So have a nice day, and see you next Monday. Goodbye.
Goodbye. Thank you.